Why is this so important? Well, imagine that there is a particle moving in space, okay? Well, two-dimensional space. And it has a path. Every particle has a path. So here is your particle. It's moving along a path like that. Assuming that you know the function that describes this path, here, I'll just draw something here for you. Here is the path of the particle. Let's say it begins at when x is equal to a and it ends when x is equal to b. Question is, what is the total distance that the particle has traveled? If we know the equation for this path. What's the distance? How much is this? What's the length of this arc? See, that's a question that wasn't answered ever, I think, in algebra or in calculus or pre-calculus. We know how to find the distance between 2 points. This distance we can find, okay? We can, but the particle, who said the particle's traveling always in a straight path? It could travel in a curved path like that, or it could travel in some weird path. So how do you know how much distance it's traveled? Or what is the length of this arc of this function? So we want the length of the arc of the graph of y equal to f of x from x equal to a to x equal to b. Now, when you get to math 8 and math 11, of course, they introduced time into the function. They described x as a function of time and y as a function of time because movement depends on time. This doesn't have any time variable in it. It doesn't. You're just trying to relate y and x, the horizontal and the vertical position of the particle. Okay? We are just going to keep it simple. Time independent, pretty much. But we want this length. So how do you find lengths and distances in R2 in plane? You use the Pythagorean theorem, right? If you took pre-calculus, the formula for distance between 2 points comes from the Pythagorean theorem. I think for some of you, I proved that formula, the distance formula. But here, arc length is also related to Pythagorean theorem. So how do we use Pythagorean? Pythagorean theorem is for a right triangle, and it finds the measure, let's say the measure of the hypotenuse of a right triangle. Okay, so here's a right triangle. The hypotenuse of a right triangle is straight. It's not curved, okay? It is straight. So what you're going to do is you are going to zoom into this curve, just a segment of the curve. Zoom in long enough so that the segment or the arc of the curve looks straight. We could do that, like we know Earth is curved, right? Earth is not flat, but to us it does look flat because we are very local, okay? We are not looking at it from a global perspective. We're looking at it from a local perspective. So just zoom in to a neighborhood of some point so that you don't see a curvature anymore. Like right there, I can zoom in. Look at that. When I zoom in, I can't zoom in long enough, but it does look like almost a straight, or it looks like a segment. You don't see that curvature anymore. Y'all know what I mean, right? Look at that. That looks like a segment. No curvature. Okay, so let's do that. Let's say I zoom in to, let's say this neighborhood right here. So to me, that looks very straight, okay? And I can use the Pythagorean theorem. So how do we do that? Well, draw a right triangle, okay? Here, I can draw the horizontal leg. I can draw a vertical leg using red. All right, now the measure, I'm not happy with this. The measure of the horizontal leg is basically just an increment of x. A tiny increment of x, and this is a tiny increment of y. So this is really delta x, or you can call it dx. That is a delta x. And as I said, this tiny increment, by the way, the book does this using Riemann sums. I'm not, it's gonna take forever. That's just a delta y. Okay, so if I draw that triangle down here, my delta x and delta y, this is the hypotenuse. I am interested in the hypotenuse. Now that hypotenuse, I should probably make this a little bigger. The hypotenuse is an increment of the arc. This is just a part of the curve. It's just an increment of the arc. So I'm going to call it delta S, where here S stands for arc length. Don't mix that up with position. You could also call it L if you want, but every book almost uses S. S is arc length. So this is just an increment of arc length. Okay, so what you do now is set up the Pythagorean theorem for this triangle, which tells you that delta S squared is equal to delta x squared plus delta y squared. Okay, this equation here is called the Cartesian metric. That's what this is, Cartesian metric. You measure things in the Cartesian system using Pythagorean theorem, but the specific equation is Cartesian metric. Okay, so what you do next is I need to somehow introduce, or if you pay close attention here, we have, of course, a delta y, you have a delta x. That has got to do with the derivative, doesn't it? The derivative, delta y, delta x. What is the derivative? Derivative of a function is delta y over delta x, right? So I am going to divide everything here by delta x squared. Okay, because if I do that, this gives me a delta x squared. I have my delta y over delta x. So divide by delta x squared. You get delta s squared over delta x squared equal to, divide that by itself, you just get 1 plus delta y over, that's delta y squared over delta x squared. I can write that delta y squared over delta x squared as delta y over delta x, the whole thing squared. Okay, and if you want, I think it would be better if I multiply everything here back by delta x squared and write the equation like this. 1 plus delta y over delta x, that whole thing squared. I'm just going to put that delta x squared back here. You'll see why in a second. Yeah, so put that right in front of the whole thing. Okay, we are basically here factoring out, if you want to think of it that way, I'm factoring out a delta x squared. See, if I factor out a delta x squared from this equation, I get this equation. I could have done it that way. Okay, but we just rewrote this equation like that. Okay, so again, this equation gives us an expression for this tiny length. Okay, take the square root. Let's just do the square root of this thing to solve for delta s, because I need the length of that little piece. So delta s here is equal to the square root of 1 plus delta y over delta x, the whole thing squared. And then the square root of delta x squared is just a delta x. It will kill the square. Okay, there is no plus or minus. We don't need the absolute value because these increments are all positive. Okay, so again, this expression here gives me the length of this little tiny arc of the curve. Okay, so if you think about it, we have a delta s, or this arc consists of thousands and thousands of delta s's. You can partition this arc like that. We can partition it. Okay, so here we have like a delta s1, we have a delta s2, delta s3, and so on. If you want to find the length of the whole thing, you add those up. We do a Riemann sum. We add them up. And if you want to get the exact arc length, you take the number of these partitions to infinity. But let me just do it step by step. So estimate of arc length, it's going to be the sum of these delta s's. Okay, you add them up, and the actual arc length is going to be, when you take this, the Riemann sums number of partitions to infinity, and when you do that, you get an integral. So you get s equal to the integral from a to b, because x starts at a, ends at b, times the square root of 1 plus. Now, when the number of partitions, guys, goes to infinity, okay, when you want to have more and more of these, the delta x goes to 0. Delta x becomes really, really small. And we call a really small delta x dx. dx is the infinitesimal small version of delta x. Okay, so instead of writing delta y over delta x, we write that as dy over dx squared. And this delta x out here becomes also a dx. So this equation gives you arc length. This formula right here is the arc length formula. And we said this comes from what section? 8.81. Let me go to 8.1, look at it. Yeah. Arc length formula. Okay. And of course, guys, our function has to be continuous. It must be continuous, else we can't find arc length. But this is it. So again, here's A, here's B, and here is some curve, whatever. Curve can look like whatever it wants. And the equation here is y equal to f of x. Arc length, we call that S, is the integral from A to B, square root of 1 plus basically f prime of x. dy dx is f prime of x squared. Integrals with respect to x. An extremely important formula in calculus and physics. Very important. Okay, so let's do a couple of examples here. What would be a good example? Circle. Can I do the integral? I don't think I can do the integral. The bad thing, guys, about this integral is that it's in almost like 99% of cases, it's impossible to do the arc length integral. There are a very few functions whose arc length you can solve for, unfortunately.
Why?
But even a line. Let's see. Let's do a line. Let's go with a line. Okay. So let's just begin easy over here. So let's say that you want to find, or let's just say here f of x is equal to 2x plus 1. Okay, and you want to find the arc length from, it's a line, right? Find arc length. From x equal to 0 to x equal to, let's say, I don't know, 2. Yeah. Of course, I don't want to use, in reality, I wouldn't use the arc length formula. I wouldn't. Because the function is a linear function, so a line is connecting the 2 points, to be honest with you. I just need the distance formula for 2 points, but we can also use the arc length formula. Okay, so let's take the derivative. You find f prime of x. It's equal to 2. The derivative of this function is equal to 2. Okay, so you just do s equal to the integral from 0 to 2 times the square root of 1 plus the derivative squared. Here's the derivative. Let me write it in red. 1 plus 2 squared dx. Okay, so you get the integral from 0 to 2, and that would be just square root of a 5 dx. Root 5 is a constant. You can kick that out of the integral, get root 5 times take the antiderivative of dx, that gives you x. So we get root 5 times x. And we're going to evaluate this from 0 to 2. And it's just going to give you 2 square root of 5. And then when you plug 0 in, you just get 0. So 2 root 5 unit, I have to attach unit here because we are talking about length. Okay? So does this make sense? Well, let's see. Let's check our work. Let's look at the 2 points. So when x is 0, again, you don't have to check on the test or for homework, but I just want to make sure you guys understand what's going on. When x is 0, plug 0 into your function, you get 1. So 0, 1 is a point on this line. And then plug 2 into your function, you get 5. So when x is equal to 2, we get 5. Okay, we want to find this distance. Okay, so this point is, the points are 0, 1, and 2, 5. Go back to elementary school. The distance formula is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. When I say elementary school, honestly, guys, I think I was like 20 something when I understood what this formula means. I'm not kidding you. I'm not kidding. I was in college when I finally understood the logic behind this formula. So when I say elementary school, I am totally kidding. But a lot of you did probably learn this early on. Maybe don't know where it comes from. But if I plug in, so here x2 is, this is my x1, y1, x2, y2. x2 is 2 minus x1 is 0, square that, plus y2 is 5 minus y1 is 1, square that. Okay, so that gives us 4 plus 16. Let me make sure I got that right. That's a 4, and then this is a 16. That's equal to root 20. And root 20 reduced is 2 root 5. There you go. So consistent. Which method is better? Obviously, this method. To me, is better. So after you're done with this class, I want you guys to think about these. Okay, I know you don't have time tonight to think about these and become all philosophical, but I want you to find a relationship between the arc length for a line and distance between 2 points. I haven't thought about it recently, but you should. If you're interested in this stuff, you should think about it. Think about how equation of a line, you got the 2 points. How is that related to the distance formula? But let's do more complex problems. To be honest with you, I was gonna use the formula to find the arc length for the length of a circle. But the thing is that when you set up the integral, you might get stuck. I think we'll get stuck. So, but let's do it, okay? Let's see if it works out or not. So example here, find the arc length for f of x equal to the square root of a squared minus x squared. That is a semicircle's equation, guys. Semicircle. And let's go from negative a to a. Let's go from 0 to a. I'm not promising this is going to work out. I don't know if it's going to work out, but we're just trying. Okay, so this is a quarter of a circle because this is the semicircle, and this semicircle is going from negative a to a, and its equation is y equal to the square root of, I did discuss y, square root of a squared minus x squared. Okay, so if I want to find the arc length, I need the derivative f prime of x. Think about it, guys. Think about this. Look, check this out, guys. Check this out. x2 minus x1 is really a delta x, huh? Delta x squared, delta y squared. Okay, and that does resemble what we have here, delta x squared, delta y squared. Just saying. That's why we need the derivative. So if I am differentiating this function, let me write the derivative out. The derivative of it is a squared minus x squared to the power of half. I'm writing it as a power because it's easier to take the derivative of. So using chain rule, you bring that half down. You do a squared minus x squared to the power of negative 1/2. Multiply by the derivative of that. The derivative of a squared is just, is it 2a, the derivative of a squared, guys?
No, it's a constant.
It's constant. Excellent. The derivative of that is 0. Imagine this is just a 9. The derivative of it is 0. And then derivative of negative x squared is negative 2x. Okay, so these cancel out. And we end up with negative x over, yeah, move this down, it becomes a positive half. And if you want, you could just leave it as square root. Okay? Yeah, I don't think this is going to work out. The integral is not going to work out. It's not, unfortunately. But let's just keep going. So the arc length is going to be the integral from 0 to a. Okay, so we're looking at quarter of a circle here. Okay, and whatever we get, we can multiply by 4, and that gives you the circumference of the circle. And again, I don't think it's going to work out. So we do 1 plus, the formula is 1 plus f prime of x squared. And here is f prime of x squared. And there is a half here. We're squaring that. The good news is that the half is going to go away. Okay, so we get 1 plus, square things out, that becomes an x squared. The negative becomes a positive when you square it out. This the square will drop out the square root, and you just get a squared minus x squared in the bottom. Dx. Okay, so that thing is the derivative of the square of the derivative. So what do we do next? Well, we got this integral to deal with, okay? And again, integrals are almost impossible to do, almost always. So let's see if I can simplify this maybe a bit. I have 1 plus this fraction I can add the two fractions by getting a common denominator. Okay, so the common denominator here is a squared minus x squared. What you do is you make this one a squared minus x squared because of the common denominator. And then we have plus x squared. Yeah, this is just not going to work out. It's not. The x's here cancel out. And that gives us the integral from 0 to a of, yeah, unfortunately, not going to work out. When you take the square root of a squared, we get a is positive. You don't need absolute value. And then in the bottom, we have the square root of a squared minus x squared dx. And this is where I have to stop, guys, because I can't finish the problem. And it's okay if I can't finish the problem. I can also always ask you to leave it in integral form. But I can't do this problem because, first of all, I have an integral with a composite integrand. This is a composite function. It's the square root of. So I have to do a u sub. For my u sub, I let u equal to a squared minus x squared. The thing is that I have to have the derivative. Remember what I taught you guys. When you do a u sub, to solve the integral, du is, again, the derivative of a squared is just 0. So we get negative 2x dx. This integral is, the integrand is missing an x. I can't do the substitution because I have nothing to substitute for that. If I had an x here, I would have been able to solve the integral, but I don't. The derivative of the inside function is not sitting in the integrand. See, we typically divide by that too. We get negative 1/2 du equal to x dx. X dx is missing here, so I can't solve the integral. I can't, but this is the integral form of the answer. Okay? Yeah, with arc length, almost 100% of the problems are not going to work out when you're finding arc length. The integral is not going to solve. There is something about the integral for arc length that's kind of difficult because we have the square root. Whenever you have integral of square root of a sum involved, we typically can't do substitution unless there's an x sitting out there. And for some of you who wonder, can you take the square root of these separately? No, we can't. We really can't do that. So if we could, you could have solved the integral for sure, but we can't. Okay, so we'll take a break, come back, and I'll just do a couple of functions whose integral can be calculated. But yeah, go ahead.
I have a question. I'm still a little confused on how the antiderivative of dx is x.
The antiderivative of what is what?
Dx is x.
Yeah,
how does that work?
Got you. The antiderivative of dx, think of that as the antiderivative of 1 with respect to x. Dx is the same as 1 times dx. So now you ask yourself, the derivative of what is equal to 1?
Or just x.
Yeah, this is equal to x plus some constant, but it's a definite integral, so you don't have to write down the constant. So you can check if y is equal to x, just forget the c for a moment. If y is equal to x, then dy over dx, the derivative is equal to 1, which gives you what? Dy equals dx. You know, so the antiderivative of dx is equal to x.
Okay.
Antiderivative of 1 is x because the derivative of x is 1.
Oh, okay. So there's a 1 there.
Yeah, the
Yeah.
antiderivative,
Okay, that makes sense.
the antiderivative of dx is the same as the antiderivative of 1 times dx. There's a 1 there.
Oh, okay. Thank you.
Guys, come back at 9:36, please. All right. So, hey, what time did I say the practice session?
You said like 30 minutes after class ends.
Okay.
Yeah, like 11:30.
Oh, yeah. I guess that's a good time. That's when my mother-in-law's here, so I want to be in the room, not go out. So that's a good time. Yes. Hiding. I'll be hiding in this room, teaching you guys. Yeah. So if you wonder though, oh no, that went on record. Oh no, I didn't pause record. Oh, shoot. I did not pause record. Okay. Oh no. All right. So if you wanted to calculate the integral here, you can't. Okay, but if you wonder what the value of this integral is, well, we can easily get it. I don't need any of this jazz. I don't. Because we know that this is a semicircle. So there. And since I'm just gonna erase that. Erase the half of it. Since we want the integral from 0 to a, that's just quarter of the circumference of the circle. Okay, so this is really 1/4 of the circumference of the circle of radius a. So 1/4 times 2 pi, radius here is a. So that gives us what? Pi a over 2. You see how easy it was solving that integral? Pi a over 2. Yep. Isn't that cool? Well, this is assuming that we know the circumference of the circle, right? We already have the knowledge of the circumference. But am I going to ask you guys stuff like this on the test? No, I'm not. I'm not. Just this is the type of question I would probably ask. So let's just do an example out of the book. Because I can't make up problems since the integral is not easy to do. So let's say we have this function y equal to, not really an interesting problem, but we're gonna do it for the sake of the integral, that's all. X cubed over 3 plus 1 over 4x. And x is from 1 to 2. So we want to find arc length again. Okay, so you find the derivative dy dx here. First of all, y, let me write y like this. Y is equal to 1/3 x cubed. I'm just rewriting y plus, if you don't mind, we can write that 1 over x as x to the power of -1. I'm writing as a power function so I can take the derivative using power rule. Y prime is just going to be 1/3 times derivative of x cubed is 3x squared. Okay, plus 1/4, the derivative of x to the -1 is negative x to the -2. The 3's cancel out and you get x squared minus 1 over 4x squared. If you just make that exponent positive, that's what you get for f prime of x. Okay, so again, here arc length is the integral from, in this case, a to b. I'm just going to write the formula. 1 plus the derivative squared, 1 plus f prime of x squared, square root of that, dx. Plug in. X goes from 1 to 2, the square root of 1 plus. Okay, we have the derivative. The derivative here is x squared minus 1 over 4x squared. That's our derivative. Okay, square that. Take the square root of the whole thing. And then take the integral. So to be able to evaluate this antiderivative, which I am assuming that it works because it's a problem out of the book, we have to square this thing. So just go with the order of operations. Don't just begin taking antiderivative as is. You have to always simplify the integrand, rewrite it, and then see what you have to do. So we're just going to do the algebra for now. Square. X squared plus x squared minus 1 over 4x squared. So when you square this quantity, remember the shortcut formulas for squaring special special squares. For instance, if you have a minus b squared, that's a squared minus 2ab plus b squared. When you FOIL out a minus b, that's what you get. So I'm going to do that on the square here. So you just do square of x squared. That gives us x to the 4. Okay, minus 2 times a is x squared, times b is 1 over 4x squared. Okay, so it's just a fast way of FOILing out. And then we have plus b squared here. B is 1 over 4x squared. Square that, you get 1 over 16x to the 4. Okay, so what I have written in orange is the square of the derivative. Okay, add like terms, simplify, things simplify here. The x squares cancel, for instance. So we have the integral from 1 to 2 of the square root of 1 plus x to the 4 minus the 2 and the 4 cancel or reduce. You just get 1/2 for that product. Okay? Just going step by step order of operations. I simplified that. Now I'm going to add like terms. So we get the integral from 1 to 2 of, and let me write in descending order. So x to the 4 is the highest term. I write that first. Okay? And then we have 1 minus 1/2. That's a 1/2, positive 1/2. And then I have 1 over 16 x to the 4. This is in descending order because you might say, hey, 1/2 is the term with the smallest power. No, that's not true, because the power of 1 over 16 x to the 4, the power of this term is -4. This is power 4. This is power 0 because it doesn't have x. And this is power -4 because of the x to the 4 being in the denominator. So this is in descending order. Okay, now what do I do with that? I mean, I'm done with all the algebra, it seems like, with simplifying all the stuff under the square root. What do we do with that? Well, see if you can simplify more. First of all, guys, I'm mentioning this again. You can't take square roots separately. Don't do square root of that plus square root of that plus square root of that. You can't break up a square root. If you do something like that, again, that tells me that you're just so miserable at algebra. Okay, don't do it. We can't break up a square root. I've mentioned that before, and I know it's really tempting. We can't do that. Okay, this is wrong. But here's what you do. When you see three terms, like a trinomial, what you want to do is most likely factor it out. 3 terms should remind you of a quadratic. Exactly. It should remind you of a quadratic. We can factor some quadratics out. Okay? Especially if these are perfect squares, and they are perfect. These are perfect squares. X to the 4, 1 over 16 is a perfect square, so is x to the 4. Open up 2 parentheses like that. It's a perfect square, so you don't really, you really don't need to think much. You really don't. To get this x to the 4, since it's a perfect square, I need an x squared and I need an x squared. To get this 1 over 16 x to the 4, I need a 1 over 4 x squared. To get the 16, you need 4 and 4. I need 1 over 4 x squared. This is the factorization. So again, anytime you see 3 terms in a sum, and the first and last are perfect squares, you can factor it out this way. Okay, you can check. If you FOIL this back, you're gonna get exactly this. Okay, you can check. Look, x squared times 1 over 4x squared. If I multiply those two, the x squares cancel out. If I multiply these two, the x squares cancel out. So I have a 1/4 plus a 1/4. That gives me the middle term. That's how you check. But again, don't think too much with these. Just do it. So anything times itself, x squared plus 1 over 4x squared times itself, is that thing squared. So what I really have here is the square root of x squared plus 1 over 4x squared, quantity squared. taking the square root of that. Good news, we got the square root of a square. They just, in a way, cancel each other. You get the integral from 1 to 2 of x squared plus 1 over 4 x squared. Okay, so square root of the square, they just in a way again cancel each other out and you get what's inside. Okay, and okay, so our integral turned into a integral of a combination of power functions. This is a power function. This is a power function. You don't see it, I can rewrite it. That's x squared plus, again, this is 1 over 4 x to the negative 2. Write it as power form, or write it in power form, and now you can take antiderivative. 1/3 x cubed plus I have the 1/4. Add 1 to negative 2, you get negative 1, and then you have to divide by that new power. And this goes from 1 to 2. Fundamental theorem. Okay, so just plug in 1/3 times 2 cubed. And here I have a negative 1 times 1/4. So that's just negative 1/4. Okay, and x to the negative 1 is the same as 1 over, maybe I should just rewrite it for you guys. Yeah, so that's minus 1 over 4, x to the negative 1, x goes in the bottom, power becomes positive. Now plug in. So plug 2 in there, you get 8, minus plug 2 in there, you get, oh, you get also 8 down there. Minus plug 1 in, we get 1/3. Plug 1 in, you get 1/4. And the rest is just arithmetic. So we have 8/3 minus 1/8 minus 1/3 plus 1/4. Just get a common denominator and add these. What's the common denominator? 3, 8, 4. 24. 24, right? Yeah, 24. So the LCD is 24 because 24 divides all of these. Okay, you can divide 24 by all of that. To get this, to make this a 24, you need to multiply by 8. So you got to multiply that by 8. You get 64. To make this a 24, you got to multiply that by 3. So multiply 1 by 3. And then multiply that by 8. 8. And that has to be multiplied by 6. So this part I really can't do in my head. 64 minus 3, that's a 61. Yeah, 61. I have a minus 8 plus 6 minus 2. So 61 minus 2 is 59. Yeah.
Professor,
Yeah.
here always the square root of u2 is equal to positive, yes?
Okay, yeah, good question. So the square root of, it seems like I skipped over that detail, but square root of a perfect square is absolute value of square root of u squared is equal to absolute value of u. So you might say there should have been an absolute value here. You're absolutely right. But the thing is that we don't need the absolute value if u is already positive. Okay, so this is equal to u if u is positive. And we know that this thing is positive always because these are perfect squares. See, square, square. So if I were to put absolute value here, it's redundant because those are there's no way these are negative. So no need for absolute value. And that does typically happen with these problems.
Thank you.
Any questions? So I on the test tomorrow, probably the problem for arc length is going to be almost identical to this problem, almost. Okay, where you end up with a trinomial like that, and it for sure factors out. Same process, same procedure, different values. So I'm telling you guys what is going to be on the test tomorrow. Okay, that's that. So that's arc length. Very important, again, in physics and in multivariable calculus.